Humanity's future is glorious. As we master space travel, we'll hop from one cold dead world to the next, terraforming as we go. Life will blossom in our path and eventually the galaxy will shimmer with beautiful Earth-like orbs. I mean, maybe. Sounds a little science fiction-y, but it wouldn't sound so far-fetched if we proved we could do it at least once. If we successfully terraformed Mars. We already have the technology to bring humans to Mars and to set up small settlements, or at least we could do within a generation. But those settlements will need to be cocooned, shielded against the deadly cold, the intense radiation, and the fatal lack of atmospheric pressure. Surely, if we want to thrive on Mars, to turn it into our second home, these settlers, or their descendants, will need to be able to open the airlocks, shed their spacesuits, and step out onto a survivable surface. We'll need to terraform Mars as our first step to terraforming the galaxy. Terraforming Mars has long been a science fiction dream, from Kim Stanley Robinson's Mars trilogy, to Total Recall, to the Red Faction game series, to Elon Musk's Twitter feed. But what would it really take? How science fiction-y is the whole concept of terraforming? In the end, it's a question of atmosphere. Mars's current atmospheric pressure is 0.6% that of Earth, and that means circulatory shutdown within a minute for an unprotected human. But it also means almost no greenhouse effect. Light from the sun, which is already fainter due to Mars's distance, is radiated directly back out into space. On Earth, that same light first bounces around in our thick atmosphere, heating it up. At an average of -60 Celsius, water freezes on Mars, but even if the planet were warmer, liquid water would still be impossible in that thin atmosphere. It sublimates directly from ice to gas. And of course, Earth's atmosphere protects us from harmful cosmic rays and the most dangerous ultraviolet radiation from the sun. All of that bad stuff has a direct path to the Martian surface. So, the most important step in terraforming Mars is to give it an atmosphere, ideally as close to Earth's as possible. In the imaginations of sci-fi writers, all we need to do is unlock the planet's latent potential. After all, Mars was once a warmer, watery planet with a much thicker atmosphere. I mean, that's conclusive. Our rovers and orbiters have found incontrovertible evidence of an ancient watery surface. The hope then is that this water and the atmosphere that once supported it is now all locked in the planet's crust and ice caps. We just need to release it. Surely we can just nuke the poles, melt enough carbon dioxide and water vapor to kickstart a feedback cycle of greenhouse warming, and that'll release more gases, and voila, Earth 2.0. Okay, not so fast. There's a real risk that Mars actually lost its atmosphere to space rather than absorbed it into the surface. The issue is that the planet is relatively puny. At 11% the mass of Earth, it has a weaker gravitational field that grips less tightly to an atmosphere, and that small size means that the Martian core cooled down more quickly than Earth's core, solidifying long ago and shutting down its global magnetic field. Earth's magnetic field protects us from the solar wind, as we saw in a recent episode. The unprotected and loosely bound Martian atmosphere may have been slowly shaved away by that wind over billions of years. And in fact, that is exactly what happened. The ablation of what is left of the Martian atmosphere has now been directly observed by NASA's MAVEN spacecraft, as we've also discussed before. And the lack of atmospheric material in the crust has been confirmed pretty conclusively by observations of the Martian surface. In a nice Nature Astronomy article last year, planetary scientists Bruce Jakosky and Christopher Edwards calculate the plausibility of using the remaining surface carbon dioxide to replenish the Martian atmosphere, based on observations of NASA's Mars Reconnaissance Orbiter and Mars Odyssey spacecraft. They focus on CO2 because it's the only plausible greenhouse molecule in any significant abundance on Mars. They assess whether release of the accessible CO2 reserves could get Mars anywhere near Earth's atmospheric pressure. And unfortunately, they conclude that no near-future technology could hope to kickstart the recovery of any useful atmosphere. But you know what? Let's go ahead and run the numbers real quick, because maybe something is still possible. After all, these researchers only ruled out near future technology. What about medium future, far future? So there are three broad sources for CO2 on Mars. First, there's the South Polar Ice Cap, which consists of water ice several kilometers deep, interspersed with thick layers of CO2 ice, discovered by radar soundings with the Mars Reconnaissance Orbiter. If all of the polar CO2 were released, it could maybe double the current amount of CO2 in the atmosphere, which is a factor of around 100 times too low to make a difference. And by the way, that CO2 couldn't be released with nukes alone, it's too deep. Sorry, Elon. The second accessible source is CO2 absorbed into the surface dust, the regolith, up to 100 meters deep. Unlike, for example, Earth's permafrost, this stuff wouldn't just melt under global warming, it would shift in its equilibrium over 10,000 years to release a small fraction of its CO2. At any rate, even if we managed to heat the entire regolith across the entire Martian surface, we'd only get 4% of the Earth's atmospheric pressure. The final CO2 source is carbonate minerals in the crust. These carbonates would need to be mined and processed by heating to around 300 Celsius. But complete strip mining of even the largest carbonate surface deposits on Mars probably get you less carbon than melting the polar ice caps. So much for near-future accessible carbon. But those carbonate minerals probably exist in much larger quantities deep beneath the surface. And that's really our only hope to find enough CO2, or really any native Martian material, to replenish the atmosphere. Let's do a quick calculation to see what it'd take. First, let's pretend there's an accessible layer of limestone, calcium carbonate, across the entire surface of Mars. There isn't, but hey, we're dreamers. We need about 10,000 kilograms of material per square meter to duplicate Earth's atmospheric pressure. Seriously, that's how much atmosphere is above your head right now. No wonder it's so hard getting out of bed in the morning. High density limestone is 2,500 kilometers per meter cubed and yields 44% of its mass in CO2 when heated or exposed to acid. So, to get 10 tons of CO2 for every square meter on the surface of Mars, you'd have to dig down over 10 meters across the entire planet. That's a few quadrillion tons of rock. I hope you have your diamond pickaxe ready. In reality, of course, we'd need to first locate and then dig down some kilometers before we could access most of the carbonates. Extracting such a quantity from depth is hard enough, but let's think about processing it. We can either heat the carbonates to hundreds of degrees Celsius or use acid to dissolve out the CO2. We'd need to process around 20% of all Martian water via electrolysis to get that acid. The electrolysis path might be better because it'd give us oxygen as a byproduct of making that acid. The energy cost in both cases is similar though, several septillion joules, several thousand times the total annual energy consumption of the entire Earth. That's definitely sounding far, far future, but not quite impossible. Finally, we have a picture of what terraforming Mars might actually look like. Let's say we want to finish this work in a single generation. We'd need to cover much of the surface of Mars in solar cells made from abundant silicon in the crust, or build 10 or so million gigawatt fusion power plants. There's really no other viable energy source. We need to channel this energy deep into the crust to power vast hordes of robotic miners/processing plants, meanwhile pumping water from the ice caps across the entire globe. This could get us a carbon dioxide oxygen atmosphere in a few decades, or centuries or millennia if you scale down the power supply to something less insane. Nonetheless, our descendants could see a Mars with sufficient air pressure and greenhouse effect to allow liquid water to persist on the surface. Now, Mars actually does have enough water for a few lakes and rivers. The ice cap water would cover the entire surface to about 30 meters, which is not enough to start a proper water cycle or have oceans, but there may be a lot more water deeper in the crust. We'd better hope so. Our brand new CO2 oxygen atmosphere is not exactly Earth-like. In fact, it's instantly and fatally toxic to humans and animals, and not so great for plant life. Certain algae can survive in a pure CO2 atmosphere, which is handy because blue-green algae, cyanobacteria, was responsible for first oxygenating Earth's atmosphere, and will need that photosynthesis because otherwise oxygen will be quickly leached from the atmosphere as it oxidizes the surface. So there's our next snapshot of the far future of a terraformed Mars. Brand new oceans green with photosynthesizing, probably genetically engineered slime, and perhaps eventually a breed of post-humans genetically or even cybernetically adapted to deal with the CO2 atmosphere. I just described the easy path to building an atmosphere on Mars. It may be the only way to do it using only Martian materials. Variations are possible, like introducing super greenhouse gases like CFCs, but that still doesn't give us the needed atmospheric pressure. At any rate, to get a true Earth-like atmosphere, we need a non-toxic filler molecule. CO2 sucks. Nitrogen is much better. It works great on Earth. But Mars has very little of this stuff. To really build an Earth-like atmosphere, we have to turn our eyes to the rest of the solar system. One popular idea is just to smack some comets into Mars. Comets contain tons of frozen volatiles, gas-forming molecules like CO2, H2O, and the presence of molecular nitrogen in comets was only recently confirmed by the Rosetta mission. But how many comets do we need? Well, assuming comets contain an amount of nitrogen similar to the composition of the pre-solar nebula, then we can guess that around 5% of a comet's mass is nitrogen. That gives the typical medium to large comet 100 billion tons of the stuff. So, to build a quadrillion ton nitrogen atmosphere, that's like 10,000 comets. Okay, so we're still in far future La La Land, but it's actually not significantly less crazy or more crazy than melting the Martian surface. What would this effort look like? Imagine this: a vast fleet of robotic spacecraft swarming the Kuiper Belt, nudging its plentiful ice balls in just the right way to send them ploughing towards Mars. Hopefully with exquisite aim, otherwise Earth is in for a pounding also. It would presumably take centuries to put such a fleet in place, and more centuries to deorbit those comets. Once Mars has been suitably bombarded, there's still a lot of work tweaking the new atmosphere. But the good news is that those comets brought with them a lot of water, so we have deep global oceans at this point. Okay, let's fast forward several centuries. Mars has an atmosphere, either released from deep in the crust or brought in from the far outer solar system. The last step is to protect the new atmosphere. We cannot restart Mars's magnetic field. To do so, we'd have to remelt the entire core. But we can try to build an external magnetic shield. The easiest would be to do that in space, an orbiting field generator placed between Mars and the Sun, like a giant space umbrella. The resources and energy needed to build this is insane, but hey, we just built an atmosphere, so why not? Honestly, all of this is pretty insane, and frankly unlikely. Would we really muster the resources to terraform Mars if we can't do the same to re-terraform Earth? But there is another option. Why build a sky if we can build a roof? Instead of terraforming, what if we para-terraform? Build what is known as a world house. We could cover vast tracts of land with an airtight bubble, or more likely, many connected bubbles. These would be tall enough to encapsulate entire cities, and importantly, plenty of Earth-like natural wilderness. Oh, and I'm still a proponent of centrifuge cities, maglev rotating habitats to simulate Earth gravity, also shown rather beautifully in this more practical design by James Telfer. If we wanted to cover, say, 10% of the Martian surface with a 300 metre tall world house, it'd require several orders of magnitude less material than building an entire atmosphere. So, say a handful of comets and/or the polar ice caps should be enough to fill our world house with air and water. Now, without a real atmosphere, space radiation is going to be a problem for our world house, as is the constant bombardment of micrometeors. People who live in glass houses shouldn't throw stones, nor live under a stone-throwing universe. But perhaps there are advanced or just very, very thick materials that would serve. So, there is our final image of humanity's future on Mars. Thousands of city-sized bubbles spread across the still barren landscape. And inside each bubble, an oasis, a lush snow globe replica of old Earth. However we do it, Mars will surely be our first step, our proof of concept, if we choose that destiny, if we choose to terraform space-time.